Okay, yeah, thank you. Things there. Yeah. Okay. So last time we talked about a partition, a total probability lemma based on the partition of the probability space. Okay, so let's first revisit that. So it says that if we have a partition of events, so this sequence of events, E1, E2, partitions the outcome space. Then for any event A, we have this partition lemma. So the probability of A can be decomposed into, we look at the probability of each partition events, and then looking at the probability of event A conditioned on these partition events. And then we sum all the terms together. Right, so in this way, we can decompose this event into a bunch of conditional events. And in many cases, in many problems, this partition is naturally constructed based on the specific problem that we're looking at. And today we are going to talk about another very important called Bayes' rule in the probability theory. So basically, in the partition lemma, we partition probability of A in terms of such a conditional probability, where we are looking at probability of A given every partition event EI. But in many cases, we would like to look at, we will see many problems later. In many real life problems, we actually need to look at probability of EI conditioned on A. Well, EI is certain partition of this omega space, and we are conditioning on the event A, and this event A is the event of interest. And to calculate this one, of course, this is a conditional probability. So we can, based on definition of conditional probability, we can write down the actual form of this conditional probability. This is the ratio between this probability of disjoint event over the probability of this conditional event by the definition of event A. But in many cases, we generally do not know how to compute this probability of this joint event, and also this probability of this event of interest. We still need to decompose these two terms into smaller terms, and it turns out that in many cases, what we know is actually the conditional probability of event A given EI. So for that, we can utilize the conditional probability rule to write the numerator as, so this is the probability of this joint event. So I can write it as probability of EI times A given EI. Right. So this is by the definition of conditional probability. So if you see, so here you can see that on left-hand side, we are talking about the probability of EI given A. But once we do such a decomposition, in this representation, it involves probability of A given EI. So it's the other direction. Here's EI given A, but here we are relating this term to probability of A given EI. So this is how we process the numerator. We can decompose this probability term into such a conditional probability. And for the denominator, we can just apply this partition rule. So PA can be decomposed into such a partition, such a summation of terms. So just to avoid conflict of notation, I can use K because I already use I here. So K, probability of EK times probability of A given EK. Right. So everything is based on here is based on definition of conditional probability. Right. And then for the numerator, we still apply the definition of conditional probability. For the denominator, we apply this partition lemma. Now, in the end, so this is called the Bayes rule in the probability theory. Now, this rule builds a relation between this conditional probability, which talks about EI given A, where EI is the partition. So if we recall that partition figure, right, this EI forms a partition of the omega space, and then A is event of interest. So here we are talking about every piece of partition EI conditioned on the event A. And such a conditional probability can be related to the probability of event A conditioned on these EIs. Right. So this builds this equation builds a bridge between these two conditional probability terms. And this is how we calculate the conditional probability in practice. So let's look at some very interesting problems and see how this Bayes rule can be applied to solve these problems. And the first one is a very, very interesting problem. Well, the statement is a little bit long, but let me try to explain this. Suppose we are on a game show. Well, you are given the choice of 3 doors. So there are 3 doors. And we call them ABC. Okay, there are 3 doors. Behind each door, there's a gift. So you are on a TV show, right? The host give you the choice of 3 doors. You can choose one from them. Now, behind each door, there's a gift. The gift could be either a car or a goat. So there's only 1 car and 2 goats. You want to pick the car. from the three doors. Like, and these three gifts are randomly assigned to each door, right? So everything is uniformly at random. And you don't know, of course, you don't know where the car is. So what you do is the follows. You randomly pick a door. So you first randomly pick a door. Let's say you pick the door A. We can assume you always pick door A because these gifts are randomly uniformly assigned. So their location is totally random. Okay, you randomly pick a door A. Let's say it's A. And then the host. Now, if you pick this door, there are two doors left, right? So these two, because we have two goals, so these two doors, one of them must have a goal behind it, because you have two goals assigned to three doors. So for any two doors, there must be one door that has a goal behind it. Okay. Now you pick the door A, you don't know what's behind it, but then for the rest of the two doors, the host reveals one of two remaining doors that has a goat. Okay. So you pick this A, you first pick door A, and for the rest of the two doors, the host knows everything behind the doors. So he will look at the rest of two doors and reveal one of these two doors that has a goat behind it. So let's say the host reveals door B. So this is the door that the host reveals, and he shows to you that there's a goat behind it. Okay. So the host reveals one of these two remaining doors that has a goat behind it. So he look at these two doors and he reveals door B, which has a goat behind it. So this is a given information to you. Now you know that this door has a goat behind it. So the question is, so you know this is a goat, so you will never pick it. So in the final step, the host allows you to change your selection. Now the question is, given that now you pick door A and then the host reveals door B with a goat, now you have door C, which is still unknown, but now the host lets you have a chance to change your selection. So the question is, in this scenario, should you still stick with door A or change to door C? Which one has a higher probability to select the car? Right. So in the entire process, you never see what is behind door A and door C, right? So these doors are, both of them are unknown to you. And the host reveals one of the bad choices to you. So now it's kind of like selection between selecting one door between out of two doors. Okay. So any ideas, any intuition on this problem. But intuitively, you never see A and C, and then the car is randomly assigned. So you may think that the probability that car is located behind door A and door C is kind of the same. So intuitively, the probability of picking A and C will be 1/2, right? That's the intuition, because you never see what's behind these two doors, and the car is uniformly randomly assigned. But because of this door B, this is the critical part. The host reveals this door B, which has a goat behind it. So this is a kind of this is an event that already happens, and all of your decisions, final decisions, are made based on this event. So there's a conditioning. There's a conditioning event in the process. So we have to very carefully analyze this problem. Right. So is this process clear to everyone? Seems a complicated one. So you basically pick a door, and the host reveals one of the other two doors that has a goat, and then he allows you to change your selection, right? So the first question is, how do we define our outcome space? What is the outcome of this experiment? Well, I would say the outcome naturally is the assignment of these three gifts to the three doors. But based on different assignments, the consequence will be different. So let's say the outcome is defined as the assignment of these gifts to the three doors. So we will have the following three different cases. Either the car is assigned to door A, or the car is in door B, or the car is behind door C, right? So these are three different scenarios, different outcome. And each of them happens with probability 1/3, right? Because we assign these gifts uniformly at random. And then let's try to think about how to mathematically formulate this question into a probability form using the probability language that we learned. So here we would like to see, okay, in order to decide to pick A or C, we are actually we just need to compute the probability that A has a car, given that this B has a goat, and compare with the probability of C has the car, given that this door B has the goat. Because this event is revealed by the host, so we know that door B has a goat. So let's define event B as host reveals door B with the goat. Okay, so this is the event that we are going to condition on. And let's define event A to avoid conflict of notation, let's define event sigma as door A has the car. So we want to compute the probability of event sigma given B. Right? Given that the host reveals this event, what is the probability that door A has the car? And we want to compare this event with its complement event. Now, given B has a goat, the complement of sigma is the event that's door C has the car, right? So given that door B has the goat, then either A will have the car or C will have the car. So we just need to compare these two conditional probabilities, and we will always choose the bigger one, right? So this is actually the problem formulation. So in the end, we need to calculate these two probabilities. Yes. Sigma complement is not door. Yeah, the car is not in A, behind A. But given B, condition on B, what is B? B says that door B has the goat, not the car. Condition on this event, this complement is simply that car is not in A means car could be in B and C, but we are conditioning on this event where door B has the goat. So the only possibility is that door C has the car. Yeah. So this means that door C has the car.
I just had a quick question on the notation of the events in sigma.
Mm-hmm.
Or I guess not sigma, the very top event. Trying to remember its name. The event with all the events in it.
Omega? This
Yeah,
one?
omega. Yeah, sorry. The three events inside of it, what do each of those mean? Is it just door A, door B, and door C?
Yes, this corresponds to the assignment of the gifts to the three doors. So this means A has the car, B and C has the goat, right? So,
Oh, okay.
yeah. So this is car, and this is goat. Yeah. I'm sorry for the confusion. And then this means that door B has the car. The car is behind door B, and this means this outcome means door C has the car.
Okay, no problem. I knew it intuitively what they might mean, but I was just confused how we got there. But now that makes sense.
Okay, yeah. So these are the outcomes. And then this event B is revealed by the host. Host tells you that door B has the goat. So you will never choose that. So the only option you have is A and C. Now the question is, what is the basically, in order to make a decision rigorously, right? You just need to evaluate, given this event happens, given this B happens, what is the probability that A has the car? Now, given this B happens, what is the probability that C has the car? And in this case, turns out this event is simply the complement of this sigma. So in the end, we just need to calculate these conditional probabilities. And then this is where we need to use the Bayes rule, because event B is the kind of the event of interest, but sigma, if you look at events sigma, naturally, it is one of the partitions of omega, because sigma says door A has the car. So basically, this is sigma. And then naturally, you can see that the entire omega space naturally forms can be partitioned into these three events. Right? These three events, they are mutually exclusive. They are and their union forms the entire omega. So this naturally gives us a partition of omega, and sigma is basically one of these partition events. So we are looking at the probability of the partition event conditioned on some event of interest. But if you go back to the Bayes rule, here we are exactly talking about the probability of each partition event given the event of interest. Okay, so let's apply Bayes rule to compute this. So first of all, based on the okay, I think we can just refer to the Bayes rule. Let's go back to the Bayes rule. Okay. Right. This numerator is the probability of a joint event, and that joint event can be decomposed in this way, according to the conditional probability. So here we are looking at the probability of B given sigma. So this is the numerator. And let's actually call this sigma A. Okay, so to make it more clear, sigma A. And then I will call this event sigma B, right, and sigma C. So this index denotes the location of the cars, basically. And in the Bayes rule, the denominator is that partition lemma's probability of E sigma K and now we have three partitions. K could be A, B, and C, right? A, B, and C. Now, the question is this easy to compute? Right? It looks like Bayes rule is very complicated. In order to calculate this one, we have to calculate all these terms. But if we examine every single term in this fraction, we will see that every single term is very easy to compute. Now, first of all, we have these marginal probabilities. So we need to look at the probability of sigma A and the probability of sigma B and sigma C separately. And these are easy because each sigma denotes the event that a certain door has the car, right? And this is simply 1/3 because we assign the car randomly, uniformly and random to the doors. Okay. So we know that P sigma A we know that this happens with 1/3. Okay. So therefore, these terms can be calculated. And the rest of the term is this conditional probability. We're looking at probability of B given sigma A and probability of B given sigma B, and so on. So let's look at each of this one. So this is the probability of event B given sigma A. So let's translate this back into into a sentence. Basically, we're looking at, given that sigma A happens, sigma A means the car is behind door A. Okay, so this means the car is behind door A. Okay, so we actually know the distribution of these gifts. So given that the car is behind door A, the two goals must be behind B and C. Okay, so this conditional event already tells us the assignment of these gifts. Okay, given this happens, what is the probability of event B? What is B? B is that the host reveals door B with a goat. So in this case, we can see that this seems to be 1, because if A has the car, then door B must have the goat. Okay, so this happens with probability 1. And then looking at the second case, sigma B means that the car is now behind door B. Okay. If the car is behind B, and then this event B can never happen, because event B means that the host reveals door B with a goat, but now the door B has a car in it. So this happens with probability 0. And the last case is, well, the car is behind door C here. Actually, let me think about this carefully. Sigma C corresponds to so the car is behind C. Something's wrong here. Let me think about this. Something. I think this is correct. And then we're looking at if the car is in A, yes, that's I don't get it now. Let me look at what is B. So I think this sigma A indicates that this is the assignment of keys. This is correct, but maybe I misunderstand B. B is the host reveals door B with the ghost. So we pick A. Now we're looking at this conditional probability. So ECG. The second one matches what I have on the note, and the third one, GGC. This conditional probability. Okay, for this one. I think I need to rethink. I need to think this for a little bit. Yeah. I think there are some misunderstandings here. I think the node should be correct, but somehow I didn't get it now. So given this assignment of gift, what is the probability that the host will store B with a goat behind it? Sigma A means store A has the card. Yes, and the assignment is clear. And then you look at post reveal store B. I'm thinking that yeah, I didn't see why is 1/2. Well, I think let's so on my note it says 1/2, 0, and 1, but I don't see why. And the second one makes sense to me, but the first and last one does not make sense to me. So the last one says the car is in C, but we're looking at the probability of that the host reveals door B with a goat in it. I guess these two should be exchanged. This should be 1/2, and this should be 1. Let me think about this. I think this should be 1 because no matter which one you choose, no matter which one the host choose to reveal, you always get gold. So this should be 1. And this one, there's a gold and a car. Yeah. That's so probably choose either to hold position B or position C. Right. Right, but I think there's a mistake there because in this case, B and C, both of them are gold. So no matter which one the host chooses to reveal, this should be one, right? But this one is 1/2 because there are, now you pick A, now the other two has a gold and a car, and the host will choose one to reveal. So it is possible that let's see the comment. Yeah, I'm trying to figure out if the lecture notes is incorrect or I'm thinking the incorrect way. So now these two has a car and a gold. So you have 50% of chance to pick door B.
But given that a car is in door C, doesn't B have a 100% chance to have a goat in it?
Right, that's what I originally think. Yeah, I'm still I don't see a very clear argument here. I think I misunderstand something. Yeah, let's all think about this. Because I believe the note is correct, but somehow, well, this problem always it's very easy to confuse people. Yeah, I got stuck a lot of times when I teach this course over the past years. So every time I have to rethink about this problem. So let's put it aside and think about it for a while after the class. I think I may need to define all the events more clearly. Maybe there's something missing there. But this idea is clear. So once we apply the Bayes rule, each single term can be calculated following the basic probability rules. But now somehow the setting is a little bit confusing. But I do want to. So we'll come back to this one in the next lecture. And if you find a convincing explanation, please send me an email, and I would like to know your thoughts on this. Yeah. Okay, let's consider a communication example. I think this one will be easier. So we have we are transmitting a message over the channel. We are transmitting a bit, binary bit T. Send over the following channel. So this channel is generated like follows. So we first generate this binary bit. It could be 0 or 1. The transmitted bit could be 0 and 1. And when we generate it, this is how we generate it. We generate T to be 0 with probability 0.4. And we generate T to be 1 with probability 0.6. Okay. So this message itself is a random message. 40% chance to get 0, 60% chance to get 1. Now, once the message is generated, let's say if it is 0, then it is transmitted over a noisy channel. So we are sending a 0 over the air. And this on the receiver side, we may get either 0 or 1 based on the channel conditions, right? The signal may be corrupted by some random noise. But here's how we describe the channel. The probability of the receiver, we denote the received bit as R. So if we transmit a 0, if the transmitted message is 0, now condition on this case, the probability that the received message is also 0 is 0.9. Okay, that means if we are sending out a 0, we have 90% of the chance to get the right message. And of course, the other case is 0.1. Right? The other case means we are sending out a 0, but we receive 1. Or at least 2 are complementary to each other, so it's 0.1. And now, and on the other hand, if we are sending out 1, if we send out a message 1, then the probability that we receive the message 1 correctly is 50%. So, and then you can infer that the probability, if we send out a 1, the probability that we get a 0 is also 50%. These two are also complementary to each other. Okay. So the entire system is now well defined. Okay, we are generating a message based on this random rule, and then depending on which message we generate, the receiver side will have different chances of receive either 0 or 1, depending on which message we send. So we have a couple of questions. What is the probability that we receive a 0? It's the first question. What is the probability that we receive a 0? Well, you can see from this diagram that there are 2 cases that we can receive a 0. Either we are sending out a 0 and then we receive a 0, or we are sending out a 1 and somehow we receive a 0, right? So these 2 naturally gives us a partition. So we will decompose this probability of this event into based on the partition lemma. So we're looking at there are 2 cases. One is that the transmitting message is 0, and then we receive a 0 given this transmitted message. The other case is that we transmit a 1, and then given that we transmit a 1, we receive 0. Okay. So these are the only 2 cases. And then each probability is given. We transmit 0 has probability 0.4, and given that we transmit 0, the probability of receiving 0 is here. It's given as 0.9. So it's multiplied by 0.9, and this one is 0.6 multiplied by. Okay, we are sending out a 1 and we are receiving a 0. So that should be this one. We are sending out a 1, but we receive a 0. So it's 0.5. So the final result is 66%. Okay. So on the receiver side, we will have 66% of chance to receive 0. Yes. We are using the partition lemma. So basically, these two events forms a partition. Okay, so let's start with outcome space. So the outcome space is basically all the possible transmitted message and received message. Okay. So it's basically 0, 0, 0, 1, 1, 0, and 1, 1. Okay. These are all the possible outcomes of this random experiment, because we have two different randoms. One is T may be random. The other one is the received message R. Okay. Both of them are binary. And then we are looking at the probability of R equals to 0. So we define the partition. So based on this diagram, we can see that tracing back, we know that there are two cases that can cause received message to be 0. Either we send out 0 or we send out 1. So these two naturally forms a partition. So we can right. So these two is a partition of the omega space. Actually, to be more specific, this T equals to 0 means that in the outcome space, this event corresponds to two outcomes. Either it's 0, 0 or 0, 1. Because T equals to 0, we only require the transmitted message to be 0. For the receiver message, we don't care. So this event actually corresponds to these two outcomes. And for E2, T equals to 1, it corresponds to these two outcomes. Okay. And you can see that these two forms a partition. Okay. This 1, 2, 3, 4, these two events, each event has two different outcomes. They form a partition of the omega space. And then you go back and use that partition lemma. So you decompose this event into each partition event multiplied by the probability of this event conditional on the partition event. So we are using that partition lemma. If we go to the top, it's right here. This is event. This event A is now this event of interest. Yeah, if you are not familiar with the partition, you may want to write down all the details. But if you later on, if we are very familiar with all these techniques, you can just write it in this intuitive way. Now, the second question is, what is the probability that, given that we receive a 0, so this is really the interesting question that we want to ask in practice, because we never know the transmitter side. What we only know, or what we can observe is the receiver side, right? We look at the received message and try to infer what is being sent from the transmitter side. So given that we receive a 0, how likely it is that the transmitted message is 0. Right? So this is called decoding. So you receive a message and you are trying to decode the transmitted message. So decoding is basically, in information theory, in communications, decoding is basically computing this conditional probability. And if you look at this entire diagram, what we know this conditional probability. We are given T, a condition on T, we know the probability of R. But now we are looking at the other conditional probability. We want to know condition on R, what is the probability of T? Well, so this is exactly what Bayes' rule does, right? So Bayes' rule connects these two conditional probabilities. So we just apply the Bayes' rule. Now, so here, so you just apply the Bayes' rule exactly. Right? So this is basically the denominator is basically this product. So here it involves this conditional probability where we are conditioning on T, looking at R. It's different from this one. And the denominator is actually probability of R equals to 0. We don't have to calculate the numeric, the denominator in the Bayes rule because it is done in part A. Okay. Part A is actually calculating the denominator in the Bayes rule. But basically, in the Bayes rule, the denominator actually corresponds to the probability of this conditional event. But we already calculated that in the part A. Okay, so in part A, we know this point, the denominator is 66%. And for the numerator, this one we are given as 0.4. And for this one, it is given in the channel. Okay. Sending a 0, receiving a 0. It is right here. We are sending a 0 and receive a 0. So it's 0.9. And this is about 55%. So this means that when you receive the message 0, 55% of the time the transmitted message is 0. The last question is, if we receive a 0, should we decode the message as 0 or 1? But you receive a 0, you want to decode this message, but you know there are two possible choices. But basically, we just need to compare these two probabilities. These two probabilities intuitively this one corresponds to the probability that given that you receive 0, how likely the transmitted message is 0. Now this one corresponds to the case that given that you receive 0, how likely the transmitted message is 1. Whichever is more likely would be your prediction, right? So in part B, we computed that this is 0.55. So we just need to figure out this one. Well, you just follow the same procedure as what we done in part B. So you replace this one to be t equals to 1, following the same procedure. Okay. These two should be t equals to 1, and you can find these conditional probabilities in that diagram. So in the end, you can get this is 45%. Okay. So decoding. So when you receive message 0, it is more likely that the transmitted message is 0. So you should predict, you should decode t as 0. Right. So this means, yeah.
Just a quick question. If we already calculated the first one in part B, could we define the second one as its complement and just solve it that way? Where the probability of t equals 1 if r equals 0, could that be the complement of probability of t equals 0 if r equals 0?
Oh yes, yes. I think that's a much easier way to go. Yeah. This exactly is the complement. Yeah, because they are conditioning on the same event. Right.
Okay, that makes sense.
But you can also go over this calculation, and they should give the same result.
Yeah, that makes sense.
Right. So this is exactly what happens in the communication devices. Right. We compute these probabilities to decode the message. But of course, this is a very, very basic channel. Yeah, if you take any communication course, you will see a lot of examples like this, which is much more complicated. Yes.
So when you do like FDC decoding, you always say like we're tracing back to the files. I don't know if ultimately really uses kind of same to decode it correctly.
I think well, it could be much more complicated, but eventually they will have to make a decision, right? Now how do we make decisions in communication? It's always computing probabilities. We make decisions by computing. You can, well, under a specific setting, you can, for example, under this specific setting, this will be the decision rule or the decoding rule for this channel. But for other much more complicated channels, we will add many other components in the channel. So the decision rule will be very complicated in practice. Yeah. But the general idea is I think is the same. Yeah, and you can see that this channel is very noisy because after calculation, we realize that if we send out message 0, we have 45% of chance to get a different message. So this means the channel is extremely noisy. So in practice, we usually, before we send out the message, we will do some encoding. We will encode the message with some redundant information in order to fight against this channel noise. For example, the simplest strategy is to repeat this message T for 100 times. And on the receiver side, you do a majority vote. So that would be more robust. But on the other hand, you sacrifice the efficiency because you have to send one single message 100 times in order to be robust to noise. So this motivates us to develop very efficient encoding schemes. So that is another story that we will learn in the information theory. I have 40 minutes. I think I can get the last one. And this is very interesting. We're talking about disease test. So we are considering a very rare disease. Well, for this particular disease, the probability of being sick is 10 to the power of -6, which means that among 1 million people, roughly one of them will get this disease. So it's a rare disease. And then this is the testing table for this disease. Okay. For each, so on one hand, we're looking at either a person is sick or healthy. This indicates the condition of that person. On the other hand, this column, these two rows indicates the testing results of that person. Could be testing positive or negative. Okay. Now here is we are given that the probability of, so if a person is sick, the probability that he or she gets a positive test is 1. Okay. And on the other hand, if a person is sick, the probability of getting negative result is 0. These two are complementary to each other. So this basically means that for this disease, if somebody has this disease, he or she almost surely will get a positive test result, right? We call this almost sure. And then for a healthy person, he or she may still have a positive test result, but this chance is very rare. It's like 0.1%. And most likely, he or she will get a negative test result. So this setting is very reasonable. So the question is, part A, what is, well, you see, in this table, we are given the condition, we are conditioning on the health condition and looking at the testing results. But in practice, what we don't know the healthy condition, right? We don't know if a person is sick or healthy. So what we can do is to do this test and then try to infer this healthy condition. So the first question is, given that somebody has a positive test result, what is the probability that he or she is sick, has this disease? This is probably one of the most important questions what we want to ask. If we see a positive test, how confident can we say about this disease? Well, we just use Bayes' rule, right? Because we are given these conditional probabilities, but we are looking at a different conditional probability, where we're conditioning on the testing result and trying to infer the health condition. So it's Bayes' rule. Okay, so just apply that Bayes' rule formula very carefully, so you will get, writing down the formula is, this is the denominator, is the probability of being sick multiplied by this conditional probability. Well, this is given in the table. And in the denominator, we need to look at the probability of being positive. But this one, in the Bayes' rule, we decompose it as summation. We decompose it using the partition lemma. So basically, being positive, you have two cases. Either this person is sick, but somehow testing as positive, or this person is healthy and somehow testing as positive. And this is the partition. And now we have everything here. All these conditional probabilities, they are given in the table. You can find them in the table. PS, the probability of being sick, is given as this one. And the probability of being healthy, well, by the probability law, is 1 minus 10 to the negative 6. Right. So you plug in all these numbers, what you get is a surprising message. It's only 10 to the power of -3 chance. So this means that if you are testing for a real disease, even if you get a positive test, it is pretty much likely that this is the testing result is wrong, right? So even if you have positive, so this means that from here we can see the complementary event, the probability of being healthy given a positive test result is actually very big. Meaning that even if you get a positive test result, most likely you are still healthy. So you should not be too worried about the positive test. So the action you need to take is probably do more examinations and get more data to let the doctors decide if you really get that disease. But from the testing result only, it's very hard to say about your healthy conditions. This is a somewhat counterintuitive, but if you follow the probability law, right, you will get this very surprising message. And the other question we have is, if we test negative, what is the probability that person is healthy, is actually healthy? Again, you apply the Bayes rule to calculate that. So I will not go over the details, but the Bayes rule looks like this. Okay, we're looking at the probability of testing negative given healthy, where the denominator is this one. But in the table, we have this one is given as 0. In the table, this one is given as 0. So if somebody is sick, he or she will have 0 probability to get a negative test result. So because this one is 0, so this entire term is 0. So you can see these two terms, they canceled, and we get probability 1. Okay. So in this case, if you get a negative test, almost surely you can conclude that you are healthy, right? But on the other hand, if you get a positive test, most likely you are still healthy. Right? So that's a surprising message for this example, right? So this means when we deal with chances or probabilities in practice, we have to be really careful. We need to formulate the problem and really think about all these conditionings, because all the events happen in practice. They are not independent events. Most likely they are depending on something else. Okay, so I think I can stop here. So next time I will try to fix the bug in that Monty Hall problem, and the next time we'll go to independence of multiple events. Okay, so as I said, I will not hold office hours today, but if you have any questions, you can